All right, welcome again, and thanks for joining the launch of the IEA Iron Steel Technology Roadmap, which explores a transition towards more sustainable steelmaking. Today is an exciting day for us. We have a great turnaround with about 600 registered participants to this session from around the world, so many thanks to all of you. And my name is Araceli Fernandez, and I coordinate the analysis on demand sectors at the Technology Division of the IEA, and it will be my pleasure to moderate this launch today. During this online session, we'll first present the key findings from this new report, and we'll then allow some time for questions. If you would like to post a question, please use the question function in the chat box in the GoToWebinar window. Let me start by saying a few words about the IEA technology roadmaps for those that are not familiar with those. This is a series of publications that started back in 2009 and that was produced since then 35 reports analyzing how different technologies and sectors across the entire energy system can contribute to a more sustainable world. The Iron Steel Technology Roadmap we are launching today complements other parts of the IEA Roadmap series on key heavy industrial sectors and is the missing piece to provide full coverage of them, together with several roadmap reports already available that deal with the cement and chemical sectors. The next IEA Technology Roadmap that is already underway will cover the nitrogen fertilizer industry and will be released by the end of next year. Most of these technology roadmaps are global, but their findings are the aggregated result of extensive underlying regional research, modeling, and analysis, which typically includes around 40 individual regions to provide such global coverage. So with that brief context setting, let me now introduce Dr. Timo Gould, the head of the Energy Technology Policy Division at the IEA, who is going to present the overarching energy system context for the Iron and Steel Technology Roadmap. Thereafter, my colleague Dr. Peter Levi will present the specific findings of this report. So with this, Dr. Gould, the floor is yours.
Good morning. Thank you very much, Araceli, for introducing this webinar, and welcome indeed from my end to this webinar on the occasion of the launch of our Iron and Steel Technology Roadmap towards more sustainable steelmaking. The report that we are launching today is the outcome of some 2 years of work, of detailed work on iron and steel making, on the iron and steel sector. As my colleague Araceli Fernandez-Pales already pointed out, the IEA has worked on technology roadmaps for a very, very long time across multiple sectors of the energy system and for multiple different technologies as well as fuels. There have been roadmaps, detailed roadmaps on different parts of the industry sector, the transport sector. We've looked into bioenergy, hydrogen, and various different other energy carriers and fuels. We looked into roadmaps from storage to more energy efficient buildings and the like. So a very, very broad coverage of different technologies, sectors, fuels that we've been releasing for more than a decade. The technology road mapping work, and allow me this short comment on the way we are seeing this kind of technology road mapping work. It's an important way for us at the International Energy Agency to develop an in-depth understanding of different parts of the energy sector, about the future demands that are on the sector, from say iron and steel demand to various other demands that are coming onto the sector as such. It helps us to develop a detailed understanding about the technology opportunities that come with decarbonizing the various different sectors, and about the policy needs and various other considerations. Road mapping work, in the way we deal with it here at the IEA, which I think is a quite unique way of dealing with road mapping work for different sectors, fuels, technologies, has two key components, two core elements, if you want. The first one is stakeholder engagement. What we do is we carry out extensive consultations with various different experts from the industry sector in question, from governments, financial institutions, academia, from all around the world, to help inform our analytical work and our recommendations. For this iron and steel roadmap, for example, we held 5 different workshops at different points in time. On the one hand, with regional deep dives for Asia in general, for India in particular, for different parts of the Americas, and we had a workshop devoted to policy instruments and financing. So a very, very extensive consultation process that underlies this particular work. The second key element of IEA road mapping work is the analysis itself, the analytical work that we are carrying out. We do not do this here in our offices in Paris just by ourselves, but we invite key experts that we identify through our stakeholder engagement to review the way we characterize technologies for our detailed modeling work across 40 different regions in the model. We look at them, these key experts, on regional considerations that are very different depending on the country that you're talking about, and we also invite them to comment on our scenario projections. So a very detailed input that we're getting there from many stakeholders around the world. They also help us with providing a lot of detailed, relevant data sets for our internal analysis, so that we are not dealing just with the data that we have at hand that we receive from our governments, but also very detailed sectoral type of data sets that help us inform our analysis. And I would like to thank many of them who are on the webinar today. I saw the registration. Araceli already mentioned that we had more than 600 registrations for this workshop, and I'm happy to say that the turnout, as I'm seeing it here, is extremely, extremely good. So thank you very much for all of the colleagues' help who are on the webinar today, for the input we received, for the data sets that they provided to us. It's been really invaluable for our work. Now, before we go into the detailed findings of the study, let me also point out that this road mapping work is not something that we just do for this type of publication, for this technology roadmap series. We are doing this to inform all of our IEA analysis, all of our IEA activities in one way or another, the modeling work, other type of activities, sometimes directly, sometimes indirectly. And the most recent publication that has benefited from this detailed sectoral understanding is, in fact, our revamped Energy Technology Perspectives publication that we released in early September. We are very confident in this publication and in other IEA publications to talk about the iron and steel sector in such detail, on the detailed considerations that come with iron and steel, because we just carried out such detailed analysis for so many parts of the energy sector. The context of this Energy Technology Perspectives publication that we released in the beginning of September is, of course, the fact that there is a growing number of governments and companies that are making ambitious pledges to reach net zero emissions over the coming decades. We tried to understand in this particular publication, what does it mean actually in technology practice? It's also a question that we're asking in this iron and steel roadmap that complements this Energy Technology Perspectives publication that we released just 1 month ago, because we all know the big pledges, decarbonized by mid-century for a government, for an industry, but we wanted to understand what does it actually mean in practice, in technology practice, for clean energy technologies more broadly. Now, when you look at the technology landscape, it is of course safe to say that there is a lot of progress that has happened over the last 10, 20 years or so. We all know about the rise of solar PV, how government support brought solar PV into the market from the labs where they were in the 1950s towards being a major player in the power sector today, with significant cost reductions that took place on and offshore wind. Very great success stories underway. Battery costs have fallen rapidly and have enabled us to believe in longer term futures, significant futures for electric cars. The IEA, in fact, here was among the very few, if not the only agency that was saying in the beginning of the year, as the market, the pandemic broke out, that electric cars will not only be resilient to the outbreak of the pandemic, but it will actually achieve a new record sales by the end of 2020. And from the data that we are seeing this confirmed. Now, an energy transition to net zero emissions is of course much broader in terms of the technology requirements than the success stories that we have seen over the last couple of decades. In our view, there are three critical areas of attention that policymakers need to deal with, that industry players need to deal with, and my colleague Peter Levy will be touching upon all of them in the context of his presentation on iron and steel. It is about dealing with existing infrastructure. Many of these assets that we have today in our energy sector have very, very long lifetime. The iron and steel sector here is really no exception at all. It's not only about coal-fired power plants, which have lifetimes of 50 years plus, but it's also a matter of various different heavy industries. The second element is clean energy innovation, how to accelerate clean energy innovation in order to have the technologies that we need to fully decarbonize the energy sector in the long run available to the energy sector at the point that we need it, including in the iron and steel sector. And the last point here to make is really about supporting infrastructure. Generally speaking, a transition towards net zero emissions will require the rollout of many different types of clean energy infrastructure, the technologies themselves, like renewables for power generation, for example, but also a lot of supporting infrastructure, transmission and distribution lines, smarter grids, pipelines for CO2, for hydrogen, etc. There's a lot of supporting infrastructure that is required in order to roll out the clean energy transition towards net zero emissions. Now, I would like now to pass on the word to my colleague, Dr. Peter Levy, who together with Araceli Fernandez-Pales, Hannah Mandova, Tiffany Vass, and Sarah Budinis were working, or were the core team that has worked on this iron and steel technology roadmap in consultation with many experts here within the agency and with consultation of many people who are joining us today in the webinar and have been working with us over many years and will hopefully continue working with us over the next years to come. A couple of last words that I wanted to say about the importance here, about the iron and steel sector is iron and steel doesn't, as all of energy, doesn't move in isolation towards net zero emissions. When you look at the sectoral contributions towards reaching net zero emissions, the power generation sector will be the key sector to decarbonize, of course, but in and by itself, decarbonizing power will just not be sufficient. Heavy industries and iron and steel in particular will have a very strong role to play to reach net zero emissions. With that now, without further ado, let me pass on the word to Dr. Peter Levy. Thank you.
Thank you very much, Timur. Just to check if you can hear me on your end. Great, thank you. So as Timur said there and set the scene, there are some sectors of the energy system in this wedge graph that Timur showed there that are where emissions are expected to be harder to abate or get rid of than in other sectors. In the industry sector, we're talking here about the chemicals, iron and steel, and cement sectors, collectively referred to as heavy industry sectors. Heavy industry sectors use large quantities of fossil fuels for three main purposes: to generate high temperature heat, for use as feedstock, and for use as chemical reducing agents. When we look at the emissions from these three sectors, we can see that despite the chemical sector consuming the most energy, the steel and cement sectors have much higher direct emissions. And this is because of the use of fossil fuels as feedstock in the chemical sector and the large contribution of process emissions in the chemical sector. The iron and steel sector generates around 2.6 gigatons per year of CO2, which is more than the quantity generated by all road freight vehicles today. Coal accounts for around 3/4 of the final energy inputs, much of which is used as a reducing agent in the form of coke in the sector. Beyond these challenges that are broadly common to the heavy industry sectors, there are two further factors that make iron and steel a particularly difficult sector in which to reduce emissions. Firstly, the steel is a globally traded commodity, which makes it difficult for first movers on innovative processes to develop these processes and maintain competitiveness at the same time. And secondly, the sector's existing assets, as Timur touched upon in the introduction, are long-lived and capital-intensive. Without any alteration to their current mode of operation, existing assets in the iron and steel sector could lead to around 65 gigatons of CO2 emissions if operated until the end of their typical lifetimes. This is equivalent to around 2 years of energy-related emissions from the entire energy system, and would put a sustainable trajectory for the sector completely out of reach if they weren't addressed. Relative to a typical lifetime of around 40 years, we estimate that the most emissions-intensive units in the sector are currently around 13 years old on average globally. And this histogram here on this slide shows the age profile and geographic distribution of blast furnaces and DRI furnaces, estimated by taking into account the year of last major refurbishment. Plant level data are used, but the average ages correspond to regions that contain multiple countries in several cases. There's a huge concentration of capacity in China, which accounts for around 60% of iron making capacity. And much of the country's enormous fleet has been installed in the last 2 decades. Some advanced economies appear to have relatively recently renewed fleets, such as those in Europe. In these instances, it is likely that blast furnaces, like a blast furnace or another major piece of equipment, has undergone a major refurbishment. One that is often the same order of magnitude in cost as the investment required for a brand new plant, such as the relining of the blast furnace. However, it's not all bad news when it comes to existing infrastructure. There are several interventions and improvements that can be made. Incremental energy efficiency improvements, the blending of alternative fuels such as electrolytic hydrogen and bioenergy, and of course the application of CCUS retrofits when they become available. These are all strategies that can avoid the need for early retirements. The dynamic of investment cycles, whereby every 25 years or so, a plant operator faces a decision whether to renew or extend the life of a key capital-intensive asset on the site or the site as a whole, also constitutes an opportunity. If these investment cycles are strategically considered alongside the development of innovative technologies, we estimate that around half the cumulative emissions from existing assets could be avoided if new low-carbon alternatives are ready to replace them in time. Just at this point, because we had a couple of technical difficulties earlier, I just wanted to check with Araceli if the sound and picture is all right. All good? Okay. So that's a lot about the present. And what about the future? Obviously, the road mapping exercise is primarily concerned with looking into the future. And this technology roadmap uses scenario analysis to explore 2 possible pathways for the future development of the iron and steel sector. The first is our baseline projection called the stated policy scenario, abbreviated as STEPS. And this scenario basically projects forward the current trends and incorporates, where relevant, the impact of announced policies. The Sustainable Development Scenario, or SDS, is our mitigation pathway. And here the methodology is very different. We work backwards from a set of predefined climate and energy goals, and then use the resulting trajectory to explore the implications for technology. And we ask a question about what policies would be required to get us there. I'll go into more detail into the emissions trajectory of the Sustainable Development Scenario in the following slides, but I wanted to present our outlook for production in each scenario. In our baseline projection, end-use demand grows by nearly 40% by 2050, from around 1.8 billion tonnes today to around 2.5 billion tonnes in 2050, and that's demand, not total production. with the generation of scrap declining slightly as a proportion, but increasing in absolute terms. Of course, consumers do not demand steel per se, they demand the services that steel provides. And it is the stocks of steel in society, in our infrastructure, our vehicles, our homes, that provide us with these services. And as economies mature, the stocks of steel in society tend to saturate. In both scenarios we explore, the in-use stock per capita of steel grows by about 50% through to 2050, to just over 6 tons for every person on Earth, up from about 4 tons today. So skip to slide. As can be seen by the sectoral breakdown, steel remains a critical ingredient across all sectors of the economy in both scenarios, and with infrastructure and buildings being key growth segments in the future. Steel will also be a key material for the energy transition. Think of wind turbines, think of hydroelectric dams, think of railways, ships, transmission, distribution equipment. Steel is critical for all these technologies and for the infrastructure that facilitates their adoption in the energy system. Material efficiency, as I kind of alluded to there, the difference in the demand and production outlooks for each scenario. Material efficiency strategies are measures that are taken to make more efficient use of steel while still providing the same material services that consumers of steel require. These include measures taken both within the manufacturing supply chain and downstream in the design and use phases of the transport and building sectors in particular. In the sustainable development scenario, steel used to build our energy infrastructure drives up demand in particular end-use segments, with demand in the power sector in 2050 about 3 times as high as in the baseline projection, and rail infrastructure about 1/3 higher. However, these segments account for a relatively small proportion of the total end use of steel to begin with, and the increases in their use are far outweighed by the combined impact of demand reduction from material efficiency. A non-negligible portion of the demand reduction occurs in the sustainable development scenario by improving yields and reducing scrap generation. And yield improvements account for around 1/5 of the reductions in steel demand in 2050 in the sustainable development scenario. But a much larger proportion is made by changes in the design and use of certain steel products, changes that are beyond the direct control of the steel sector. Together with the direct reuse of products without remelting them, such as beams recovered from demolished buildings, changes in the way buildings and vehicles are designed and manufactured account for the lion's share, 80% of the reductions in steel demand in 2050. Overall, steel demand is about 20% lower in 2050 than in our baseline projection, so 20% lower in the sustainable development scenario. Material efficiency, though, is just one of a portfolio of mitigation strategies adopted in the iron and steel sector in the sustainable development scenario, in which direct emissions from the sector decline by more than 50% by 2050 relative to today's levels. And this corresponds to a decline in the emissions intensity of crude steel production of around 2/3 because demand is slightly higher in the SDS. When we look at the short term, it is indeed material efficiency and technology performance improvements that contribute the lion's share of emissions reductions. So more than 90% of the cumulative reductions to 2030 are attributable to these 2 measures. While these measures play critical roles, they are incremental measures and they cannot alone deliver a step change in the emissions intensity of primary steel production in particular. When looking at the whole modelling horizon through to 2050, we can see that a host of other measures come into play. Material efficiency is the single largest contributor overall at 40% of cumulative reductions. Technology performance improvements deliver around 1/5, and this category includes the adoption of best available technologies and improvements to the way processes are operated and controlled. This might be a smaller share than one might have thought, but this reflects the fact that increases in energy efficiency are already well incentivized in the steel sector. Hydrogen and CCUS together account for around a quarter of emissions, cumulative emissions reductions, which stem from the deployment of innovative technologies, which is something I'll come into in more detail on the next slide. And a series of other measures, including the use of bioenergy and other fuel shifts, including to natural gas and to electricity, contribute the remaining portion of cumulative reductions. With respect to electrification, the relatively minor role is because the shift to secondary production that takes place in the sustainable development scenario largely takes place in the stated policies scenario as well. So the delta between them is not so big. Bioenergy, as mentioned earlier, faces sustainability constraints and is in high demand across the energy system in the context of the sustainable development scenario. And although it does play an important role in certain regions like South America, where charcoal-based blast furnaces are already operating commercially. So, now I'd just like to unpack the role that each of these technology families plays by looking at the deployment of specific groups of processes in the sustainable development scenario. The first thing to note is that both primary and secondary conventional processes do still play a role in 2050, but their trajectories diverge. The scrap-based electric arc furnace route nearly doubles its share of crude steel production in 2050, while the share attributable to the blast furnace basic oxygen furnace route declines from around 3/4 today to around 30% in 2050. CCUS equipped routes, including innovative blast furnaces, innovative DRI and smelting reduction concepts, account for around a quarter of primary production by 2050, up from just one single plant operating commercially in the United Arab Emirates today. Hydrogen is used as a blending agent in DRI furnaces and blast furnaces, but much more importantly in the dedicated pure 100% hydrogen-based DRI EAF route. This route, the hydrogen-based DRI route, accounts for around 15% of primary production by 2050. These process shifts have a profound impact on the energy mix of the sector, as one might expect. Unabated fossil fuel use declines from 85% of energy inputs today to around 45% in 2050. Electricity demand surges, more than doubling its share of final energy consumption, just under a third of which by 2050 is used to generate electrolytic hydrogen. Bioenergy demand also increases its share dramatically, but as mentioned before, its overall consumption is constrained by limits on its sustainable supply. Just to note, while we're showing the kind of global process deployment and energy mix here, there is much more detail provided at the regional level in our publication, which is should be available on our website now. And our analysis is built up of this region by region assessment, taking account of policy specificities and energy price contexts in each region. Of course, the steel sector does not operate in a vacuum, and this is one of the things that Timur mentioned in setting the scene. The changes in the way that steel is produced will have significant impacts and implications for other energy infrastructure assets, and particularly the CCUS equipped routes and those making use of hydrogen. Just to recap the situation today, around 1,400 million tons, so sorry, 1.4 gigatons of iron is produced each year, virtually all of this without the use of CCUS or hydrogen. By 2050, overall iron needs have declined slightly due to increased scrap availability and the adoption of material efficiency strategies that I outlined earlier. And around 40% of the total is produced using CCUS or hydrogen to manage or avoid the CO2 generated. The CCUS equipped production implies the need for infrastructure able to capture, transport and store around 400 million tons of CO2 per year by 2050. And to satisfy this need, one large CO2 capture facility able to capture 1 million tons of CO2 per year would need to be able to be installed every 2 to 3 weeks from 2030. The Northern Lights project in Norway is a good example of a full-scale demonstration of the CCUS value chain involving different CO2 sources, including industrial ones, although in this case it's cement rather than steel that's the industry source there. The challenge is similarly impressive when it comes to hydrogen production and the infrastructure required to produce it. So around 5 million tons of dedicated hydrogen production is used in DRI units today, albeit mixed with carbon monoxide and virtually all of it without CCUS. By 2050, this volume expands to around 23 million tons, with 3/4 of this being generated via low carbon routes. The electrolytic portion of this low carbon hydrogen, which is the vast majority of the low carbon portion, or about 16 million tons in total, that's electrolytic, requires around 700 terawatt hours of electricity per year by 2050 to generate it. Besides the gigawatts of renewable power infrastructure, this would require around 165 gigawatts of electrolyzer capacity compared to around 0.2 gigawatts of capacity installed across the system today. The role of innovation, the role of innovative technologies is underscored when we look at the innovation dimension of this equation. So, taking the annual emission reductions in 2050 in the Sustainable Development Scenario, relative to our baseline projection, we can see that just under half stem from technologies that are at demonstration or large prototype stages today. This shows that deep reductions in emissions will not be possible unless the technologies currently at early stages of development are carried through to commercial deployment and rapidly scaled up. Here we can think of the hydrogen-based DRI route or the innovative smelting reduction route, currently progressing through successively larger pilot and demonstration projects. If these are not followed through, the pathway we outline in the Sustainable Development Scenario won't be possible. Now, some companies and governments have announced net zero targets for 2050, and while this is not a globally adopted goal, in our analysis, we wanted to look at into the feasibility of reaching this target for the energy system in ETP 2020 and by extension in the steel sector in this publication. For this, we used the faster innovation case. And the result is that around 1 gigaton further of emissions reductions are required beyond that in the Sustainable Development Scenario in 2050. This necessitates a step change in ambition when it comes to innovation. Technologies at demonstration and prototype stage today need to reach markets within the next 6 years, which is twice as fast as in the Sustainable Development Scenario. Technology at the small prototype stage needs to become commercially available over the next decade and scaled up rapidly thereafter. This is the case for iron ore electrolysis. The faster innovation case underscores the importance of accelerating efforts in innovation to reach net zero emissions by 2050. But it also shows that our chances of achieving such a goal would be greater if technology efforts were to be complemented by behavioral changes. Now, I just want to conclude with a word on the roles of the various actors and key enabling mechanisms required to realize the Sustainable Development Scenario as we lay it out in the publication. And I should just note that there's a whole chapter dedicated to this in the roadmap. And while we're unable to prescribe specific actions for every stakeholder and every jurisdiction, we cover in detail the current policy landscape as we find it for the iron and steel sector. And the menu of options available to accelerate progress in this area. Coordinated efforts from a diverse range of stakeholders are required, but the overarching driver of change lies in setting long-term plans and establishing a clear, reliable policy signal for emissions reductions. Here, governments will play an important role. Additionally, targeted efforts are needed for specific technology areas, including emissions-intensive technologies that will still be required for some years to come, and clean technologies that are at varying stages of development today. Steel producers will need to make detailed plans for their existing assets, and their efforts in the realm of innovation will be critical. Government support for RD&D and subsequent early deployment is also likely to be needed. A focus on material efficiency can help increase the quantities of scrap available for secondary production and therefore reduce the need for additional primary production capacity, which is emissions intensive with current technologies. Efforts from actors along the value chains from design to end of life will be important, as are the regulations to support these interactions. Finally, enabling conditions need to be put in place to create a level playing field for steel companies around the world. This includes supporting infrastructure in each of the jurisdictions, including decarbonised power units and CO2 storage and transport, and improve systems for data collection and reporting to allow better coordination between actors. Time's of the essence. We are now only 1 or 2 investment cycles away from a target of drastically lower CO2 emissions from the iron and steel sector, but the transition cannot happen overnight, which is why the next 10 years from now until 2030 is a critical window to lay the groundwork needed. During this period, it will be important to capitalise on near-term opportunities for material efficiency and for technology performance improvements, and with an eye to the longer term, there'll need to be the continued need to demonstrate the near zero technologies that are under development today. The changes won't be easy to implement, but with cooperation and sustained efforts from all stakeholders, including many of the people participating in this webinar tonight, we seem to have got up to 450, and I should say this afternoon, not tonight, including many of the people here, the steel industry is well placed to be an exemplar sector in the clean energy transition. So with that, I'll stop and pass back to Araceli, and I look forward to kind of hearing your questions. But before I do, I'd just like to thank everyone listening today and to extend particular thanks to our colleagues at the World Steel Association. They've helped not only by connecting us to all of you, but have also provided us with important feedback and input throughout the modelling and drafting process for this publication. So thank you very much to them.
Many thanks, Peter and Timur, for the extensive presentations. So we are gonna now start the Q&A session, but before doing that, we would like to hold for a couple of minutes so that all participants can post their questions. Remember to use the chat function and this send question to staff selection in the drop-down menu in the go to webinar window, so that we can receive all the questions, we can compile them, and then make sure that we can address them as much as possible in the time that we have left. So that if you could please be with us for a couple of minutes, we'll be back right away to start with the Q&A. Thank you very much.
So let's get back to the questions. Just to say, we are receiving many questions. We'll try our best to go through as many of them as possible here in this particular session, but please bear with us. We'll probably need to finish in around 10 minutes of time. So we are going to try to get through as many questions as possible. Let me just answer right away the most popular question, which has come from many different colleagues here, which is about the slides and the report itself. So let me say the report is available for free download on our website today. So it is available. It's launched today. This is the launch of this Iron and Steel Roadmap. You're more than welcome to download it for free from our website. The slides will be, after this event, will also be made available on our website as well. Let me probably start with a broader question that came here before we zoom into a couple of other detailed questions. The first one probably can be taken by Araceli. It's about the link of this particular scenario, this particular iron and steel roadmap, to the overarching temperature targets that have been set by the Paris Agreement to reach in this century well below 2 degrees and pursue efforts to reach 1.5 degrees. Can you, Araceli, elaborate on how these results that Peter just presented link to this particular temperature target?
Sure, many thanks, Timur. No, indeed. So the core scenario that underpins the Energy Technology Perspectives 2020, but also the technology roadmap, as Peter highlighted, is our sustainable development scenario, and that scenario integrates let's say the realization of 3 different sustainable development goals. One being climate change mitigation in a compatible way with this Paris Agreement, but also the allowing energy access as well as reducing air pollution. So it's a bit of an overview of those 3 sustainable development goals, which are part of that analysis. Now, the sustainable development scenario is being analyzed and modeled up to 2070 when it reaches net zero emissions, and again has a carbon budget and trajectory compatible with the climate, with the Paris Agreement. In the technology roadmap, the numbers are provided up to 2050 for consistency with the technology roadmap series that, as I've mentioned at the beginning, started in 2009, and since then this has been the time horizon that has been used. We wanted to keep consistency with that, but we've made quite a lot of cross references to the ETP 2020 work with findings up to 2070. And beyond that, as also Peter mentioned, we've wanted to have an understanding and an analysis of the feasibility of reaching net zero emissions earlier by 2050, only through the lenses in a way of technology innovation. And that is, as a result of that, we were presenting the numbers related to the faster innovation case, which again are discussed in detail in the Energy Technology Perspectives, also for the iron steel sector, and there are some of those findings also integrated in the technology roadmap. So we hope this gives a comprehensive analysis so that the readers can really understand the sensitivities of the different let's say dates by which net zero emission targets could be met at the global level.
Thank you very much, Araceli. Very helpful. Next question, maybe to Peter, is about coke, the use of coke in steel making, and whether we think that hydrogen will replace the use of coke in steel making, and if so, how long would this potentially take?
Thank you, Timur. Yeah, so we explore the use of hydrogen in 3 main areas in the technology modeling. So we look at it as a blending option in both DRI furnaces and blast furnaces, so those first 2, and then we also look at the use of the pure hydrogen-based DRI route. And these three options, the electrolytic hydrogen used in these 3 areas, contributes about 8% of the cumulative emissions reductions in the sustainable development scenario relative to the baseline projection. So that's not an entire replacement of the use of coke. There are still blast furnaces, as you will have seen in the technology penetration slide that I showed. But this is a kind of a fairly rapid rollout of electrolyzers and of hydrogen as a substitute for carbon-based reducing agents in the sector.
Okay, excellent. Thank you, Peter. Maybe just a follow-up question on this, if that makes sense. There is a question on the fastest and cheapest options to decarbonize the iron and steel sector. Can you say a couple of words about what are the fastest and cheapest options to decarbonize the iron and steel sector? Is that any different in different regions, or how do you assess this?
Yeah, absolutely. So, I mean, as I was saying on the hydrogen question, I think that it's important that we analyze the kind of full portfolio of options that are being pursued in the sector. And while I've kind of broadly and kind of simply broken these down in the presentation into sort of hydrogen-based options and CCUS-based options, there are, of course, many variations within these. If we stick with those two categories just for simplicity in answering the question, I mean, there are various regional contexts which we look at in the roadmap, and some of the results are presented for these different regions where we see different technologies having different advantages. So in areas where you have access to low-cost natural gas, for instance, it might be that the DRI route equipped with CCUS, as we see one example of it commercially operating in the Middle East today, might be a kind of more attractive route in those kind of circumstances. Equally, regions where you have access to lots of low-cost renewables, this could well be a context in which the hydrogen-based DRI route proves to be more attractive. And equally in regions where the policy landscape and storage resources and transport infrastructure that might need to be built up for other sectors is amenable to doing so, then CCUS equipped routes, whether it's the innovative smelting reduction or innovative blast furnace concepts, or indeed innovative DRI concepts with CCUS, these routes might be more applicable. For direct kind of more detailed penetrations of each route, we do provide some regional analysis of this in the roadmap itself.
Oh, thank you very much, Peter. There are plenty of questions coming in, so we will not be able to answer many of them, all of them. We will try to our best to answer as many as possible, but we cannot do all. So let me probably try to summarize two of them for Araceli, and then another one for Peter, and then we close the meeting afterwards because we're running against the clock here. The first one, or the first two ones to Araceli, is about the challenges of decarbonizing iron and steel of this particular roadmap compared to other materials, other sectors. Do we have a harder road in the iron and steel sector ahead of us, or how do you see it? And another question was here on green steel, the fact that green steel demand is so far limited. Can you say something about how, in your view, this demand for zero fuel steel can be enhanced, and what are the different options that are available? And then the last question will go to Peter about the role of international collaboration, how we envisage governments to introduce various different policy tools while maintaining competitiveness of local industries. Araceli?
Sure, many thanks, Timur. Yeah, indeed. So first, perhaps on the first question, so about whether the steel sector has a harder way to go in a way compared to other heavy industries. I mean, thinking about this in terms of the technology options that the sector has available in a way at different stages of development, of course, but also given the characteristics of steel, again, being one of the materials, for instance, that is more recycled today, for instance, and also allowing different ways in which it can be produced. I think it has a positive and optimistic kind of state of play compare to other, let's say, sectors that where also emissions are difficult to abate, in the sense that there's more flexibility on the different options that could be accommodated and could be considered. Now, having said that, it's been, as we've discussed in the presentations, Peter highlighted some of the challenges of really making the emission reductions in this type of sectors, particularly on heavy industries where technologies that would be needed are not available at commercial scale, and they have specific operating conditions or characteristics of their materials that make them particularly hard for technologies to really, let's say, provide a very low CO2 footprint. And so in our analysis, that when we look at the whole energy system, of course, all these considerations are taken into account, so that we see different, let's say, speeds of decarbonization when we compare, for instance, the power sector with some of these heavy industrial sectors. Now, within these key sectors, steel, chemicals, and cement, in our modeling, we consider the same and very similar, let's say, level of decarbonization effort or emission reductions effort. And we do this by basically modeling a similar level of reduction when it comes to the CO2 footprint of these materials. And so the starting point of these different sectors, as well as how the prospects for the demand of these different materials would be in the future, have a role to play in terms of what would be the final emission reductions in absolute terms. But the relative effort in terms of the CO2 footprint for these materials is very similar in our scenarios. The other question, perhaps to touch quickly upon in terms of how we could, in a way, stimulate or promote green steel, as just to highlight, as Peter mentioned, there's a full chapter devoted to different policy instruments and strategies, the last chapter of the roadmap. So really worth a read on that front as well. But just to highlight some quick touches on that front, in a way, there's of course different ways in which governments, but also industries can stimulate or build a market and strengthen the market for let's say green steel when direct, let's say, regulations for emission reductions may not be effective enough. There's, for instance, options in terms of governments by establishing or linking specific requirements for the CO2 footprint of the steel that is connected or demanded for specific public projects or infrastructure projects, so kind of a strategy that would be linked to public procurement. Also, we've seen also in other sectors how, as well, different companies have reached agreements along their value chains so that different customers would commit to, let's say, purchase materials that will be produced in a sustainable way, and this could be also applied to the different and diverse steel value chains, certainly. And of course, there are specific commitments as well, where industries can as well make their CO2 footprint reduction targets part of their strategy and accommodate into those strategies also labeling, communication approaches, awareness raising through with customers, etc., so that again there will be further potential for green steel in terms of the size of those markets. I will leave it here for a moment and perhaps pass it on to Peter to deal with the final questions we could accommodate before closing.
Thanks very much, Araceli. I believe we have a question here about international collaboration, and it links a bit to some of the policies and enabling mechanisms that you were just touching upon there. And I think the thing to state here is that of course it would be nice if there was just a perfectly harmonized and agreed upon global carbon price, and then all of the markets for these products for green versions of the materials that we have today would inevitably just move up to be among the cheapest available, and the market would work it all out. However, we all know that that is not something that we can rely upon coming about anytime soon, and so there are a whole host of measures that can be taken in the meantime in the sectoral in various sectors and also in various jurisdictions. There are some that we get asked about quite a lot, like carbon border adjustments and in regional carbon pricing, carbon contracts for difference is another measure that's coming up at the moment and is being talked about a lot at the moment, where the government sets a strike price and then remunerates the steel producer for any difference of the increased cost in production, to give some kind of contract security and some investment security. We can't be prescriptive about which of these measures are right for different jurisdictions, but we quite extensively outline the menu of options that are available to people wanting to affect a transition in this space. Yeah, I think that's all on my side, Araceli.
Excellent. Well, many thanks. I think I'm afraid, as Timur mentioned, we'll have to wrap it up and close the session now. But please, we've gathered all the questions you've posted. We'll get back and try to respond the ones that we wouldn't have the time to do so by email, and so that we can make sure that you have all the information needed and to understand the findings of this roadmap. Following the launch, in any case, we are going to be presenting and discussing the roadmap findings in more detail in several events with different stakeholders. So please don't hesitate to get in touch with us should you be interested in continuing this discussion. We'll be happy to organize a specific event session with you and your group. Let me now conclude the launch webinar, and by thanking again the World Steel Association for their important support throughout the development of the whole project, as well as all the organizations really and experts involved in the multiple discussions and events. And just thanks again to Timur and Peter, but also the whole and the entire industry team with Hannah, Tiffany, and also Sarah for their tremendous and tireless efforts to produce this roadmap. So with this, many thanks everyone, and goodbye. And we'll really hope to keep in touch. Thank you very much. Bye.